Okay, hey George, we're going to show them how you work. Hi George, so George is going to assist us in this one. Bruce is over there too, the right in the right. But George will be our assistant today. Hi Georgie. So let's turn it this way. And George, what do you think of this here? Yeah. Okay. So what you're looking at, this will be the column. This will be the slab up top. I'm letting you look at it in this configuration as if you can see through it. This would be the extension, the wall up top, and also the extension of the slab extending out. This is going to represent a rebar reinforcement. This is the wall, the garage wall. Alright, garage wall. And rebar, just the one section of it. It's the slab. The slab goes out to here, roughly the end of the back side of the sheet piling. But the reinforcement doesn't go all the way back there. It's not there. It's internal. How do I know that? What's left behind, the concrete that's left behind, the blowout. The blowout, if you will, the remaining cone shape. Here's our rebar reinforcement, top steel and bottom steel, with a little bit of cover, concrete cover. Again, this represents the deck. Alright, the steel has about a 12-inch leg on it, this little leg here. Well, if I do that, and the deck is 9.5 inches, you see it can't make it. It's too big, right? It's not the rebar bend is too big. You can see the gap back here. So that doesn't work. You don't get to place the steel where you need to place it. Then you got this steel that sticks up just a little bit. Right there. So now, watch what I do here. I did this in the other video where I showed you the cross bracing. This is all I'm going to do. That's all I'm going to do. And it's going to leave this, it gets set in the concrete, and when it comes out, it blasts away and leaves behind these little X shapes. These little X shapes. So now, I can still get my 12 inches. Alright. So let me look in there, make sure you can see it. I just crossed the steel a little bit. I get placement of steel top and bottom. I still get 12 inches or whatever it might be. About 14 inches, 12 inches. And I get this development like that. It's still there, got plenty of cover where these tips aren't at the edge of the concrete. They get crossed, braced like that, and you get your top steel and your bottom steel. Now let's go ahead and put this steel there, and this is back here. So this becomes like a gusset plate. This is so rigid back here, all this concrete locks it in. It becomes like a gusset plate. When this goes down, I'm going to lock that in behind there. Might take a little liberty and let it hook. When it goes down, it spalls off the concrete right there. Did you see what happened there? I'm not saying it's sliding at all. It's locked in place here with that. And if I could lock it with my finger, you'd see what I mean. As it goes down, it spalls off this concrete right here. Now some of the steel might have been anchored back there, so, you know, depending on the profile of the wall. But I would theorize not, that it's more hooked behind it like that. Alright, so I'm going to lock it with my finger. Let the deck go down, and you get your spalling and your rip off here. I just wanted to show you the cross bracing in this one. How you get that long legs into a 9.5-inch wall just by crossing them. Just by crossing them. How you get the interlock here. How you get the spalling off. And there's your little section. Okay, looks like I gotta add this detail, if you will. The bottom bar, I want you to think of this as a beam. The bottom bars are number 4 and the top bars are 5/8 with the hooks. Now the bottom bar might also have a hook. I have it, if you can see this bar right here, and I'll show it to you in the video what this means. Imagine it's just sliding out, just sort of like, it just pulls away. There's some engagement there, and that's when I engage. Maybe it's able to pull it away with that. See how it pulls it down? Maybe it's able to do that with that there. But I also have a version where they actually hook the bottom bars, which, you know, not normally done, where this makes it more likely not to fail, fracture in the back. To give me a fracture, rather, the fracture plane in the back, to give me that cone to blow it out. I'm sorry, it's still locked in. Like that. Still locked in. It gives me that blowout back there. But now I can get that blowout another way. These top bars are approximately 13 inches apart, 5/8. I think I misunderstood. 13 inches apart, 5/8. And here's your cross bracing of it. Top bar. Bottom bar is down here somewhere. So this should be the top bar. Top bar, 13 inches apart. And there's our cross bracing again in the wall. So I have it that way also. So there's a cross bracing. That cone that comes out. Down the bottom here is your number 4 rebar. This is 5/8. So a very interesting note I'm trying to get across there is that, sneak it in with you, is that this is look at this as a section this off, and you'll see beams going all the way across. I want you to where it intercepts on a column, great. Where it doesn't, let it fly. And then figure out, well, how's it being supported with that long span? And go, oh, it's being supported with the cross members from one column head to another. Clearly they line up. Facetiously, again, I'm stating that. They're an offset, and their offset creates all types of drama. And that's where you get all this torque in the stack. Because they're not. Even if they were, you still are just dealing with section it again, and you're only going to see a little bit of 5/8 off the shear heads, and then it's going to switch to 4. I want you to look at the drawings here. It says, note, bottom reinforcement shell be number 4, 1/2-inch rebar times 12, at 12-inch bottom each way, 2 directional 12-inch OCs on center, in addition to any indicated bottom steel. So if they more indicated bottom steel, then it will be in addition to that. And we're going to the back wall real quickly. And we'll scroll over to the left. So right here it says number 5, 12-inch on center. There's other notes that say 13-inch on center, just so you know. TYP stands for typical. And there's also TYPE, which stands for type. Right here, number 4 rebar at 12 inches, 20-foot lengths. Bottom additional. So it appears they want more rigid additional, it says, right? So it's in addition to that. So is this a mat over here of 2 layers at the bottom? I don't think that to be true. I don't think it's there. But right here it says 4 20-foot long lengths, bottom steel, ADD dot. Could be additional. It's also specifically right there. It doesn't mean it runs the entire length of the wall. I don't know where this would terminate, but let's just use it. This is in front of the garage, just so you know. This is the garage section. And I don't know what it extrapolates to, all right? So just want to throw that at you. Now here's the 8 number 5s, and they appear to go this direction. Very interesting, right? Now I want you to think of, remember I said section this. Section it as a 12-inch wide beam with 13-inch on center, 13-inch wide beam. And you could see how it would behave individually. You have this wall back here, this more rigid wall. Remember I said the cantilever effect. I had more to it. This is now the reveal of that. I was waiting for a challenge. No one took me up on it. Here's the 5/8, the number 5 rebar extending out. Typical again. This is addition to the bottom steel. Here's the 8/5s going that direction also. I want you to imagine the section. When you section this, I'm going to do an air ball on purpose here. Okay, so let's do that. So there's a section, let's call it 13 inches wide or 12, whatever you're happy with. You can see I make it from the wall to the wall. I bypass, I miss both of these critical shear zones. See, I'm right between them. Even miss that one. And it continues on. So I miss it. I'm on the outside of it as you run it all the way over. Now, these panels, ACI like to see them as. The steel is continuous. It's not a control joint, so I state that they all will be have a behavior which would engulf each other if it ever started collapsing. Well, mostly it did, except for by the garage there. It did break free. It didn't have enough kinetic energy to keep pulling down into the butterfly zone because it was interrupted by the corner wall and the column. So this column and this corner wall here. So the energy wasn't there for it to. It broke itself free, unzipped on the other side of this to some degree back, but not. I don't want to go into that right now. Now I'm going to shift this over at this section. Now all of a sudden you see from this section it goes over. Oh, it lands on top of a column head. Well, you never section it, so it runs that direction. Steel two directional. Now I want you to start seeing, wow, look at all the different behaviors here. As this steel goes this way, this is more like a mini beam, if you will. It's going to act in a beam capacity, stressing this more so as it tries to take the load there. And then out here, across this section here, remember it's two directional, I'm going to show you, I'm going to back that up. So this is 5/8 steel in this configuration. See the shape of it? There's I shouldn't be doing it there because there's a pull down of the hot tub. Let's do this one. Let's move it over. So right there, there's 6/5s and 19/5s. It's this critical shear development of the reinforcement is the larger reinforcement. This will be top steel, I believe, right here. And the we don't have the shop drawing, so it's as close as we get. So then I'm going to leave it at that. Shop drawings that. So here's your 90 coming down here. See the 90? So this is your 5/8, and it doesn't quite tell how far it wants the 5/8 to go. It just shows 5/8 typical, meaning you could even change it to something else because it's typical. This is not option to change. This is 19/5s by 16/5s, and then across this one are number 4s. 4s go from here. So remember I said I want you to think of the beam. This is the top. This is the number 5 steel. Okay. And the bottom is number 4. Now, normally you'd have the reversal on this, but this is over here. So this is the closest I could find in the drawings to a shop drawing. You can extrapolate what I'm trying to say by overlaying it. And I'm looking at it like an overlay here. Hopefully this helps. This is over here at this, so I'm going to slide this over here to help you see it. This is not that easy actually. Let me slide it to this one. Is it the same? Yeah, same configuration. So then, and then I'm going to grab some 4s. Now the 4s I'll run all the way over to the column head. The column head. ACI likes you to divide it per column head, so I shouldn't really be on the other side of that, except for, you know, it's anchored on the other side. It's just not a wall system, but they want you to still do the column to column head. I've got a problem with it. I can't do it. Sorry. Here's the 4. All right, I can do this one, but I can't do the top steel. So here's your 5. And this is your 4 down below. Now it goes from across the column head, continuous. See the number of 4s right here, 14 4s, 14 4s, 16 4s down here, broken up. Now, so over here are the 16 5s again, the number 5s. So I'm going to do this. This time I can do this with the 5s. So then I want you to, I'm taking some liberty. I'm showing you the full here and then a little half here. Now this is the 4 down below. That's the half of the critical shear zones. I should clarify. I'm going to push it up. I want you to see a beam here now. I want you to see this beam, this beam west to east, and you would see, okay, so they put 5s here for the negative steel, the top steel, and then the bottom they put 4s. And there's nothing connecting these top. There's no crank bars used in other countries. We don't really use them here. Crank bars like that to tie them together. Different beliefs on crank bars. There's no stirrup system to tie them together, no hooks to tie the top and bottom together. There's just concrete. And ACI says concrete is weak in tension, up to only 10% of the value of compression. I state that by them saying that they're saying Newton is a crackpot, equal and opposite reactions, right? Everything. So clearly you see here, this is Newton's third law, equal and opposite. This is by NASA. So who is correct, NASA or ACI? You tell me. Right? Everything's equal and opposite. Well, ACI has found is debunking Newton in that case, or sagging. Now let me put this closer now. So let's pretend that this makes another beam over here, rigid. This is the cantilever effect I talked about. So that's the top steel. And then I'm taking some liberty by closing it up. And that's the bottom steel, the number 4. And it's over top of the column head. So here's your column head. Let's move this over here. And let's put the 5 up. And then let's run the 4s. Now I'm going to go past it just to show you a little clarity where things are going with this. And I'm stating that this being close to here creates a more rigid plane out to, well, at least a critical shear zone. 100%, because that's the way you do these capital heads, these cap heads. So it's like a bracket, if you will. It gives it rigidity there. And then the transition happens from here, where you get your deflection. Of course, the steel on the bottom is being pulled. But now I'm going to take some liberty. I'm just going out to the edge of here's the box. See the box? And the box there. Now I'm going to give you some sag between it. Not much, because the span is, you can see this is much shorter within the span back here. So let's do, so from here to here, remember my cantilever effect says it sticks off the wall approximately 4 to 5 feet. Down here it's about 5 feet where the deck takes a different fracture plane. And up here is about 4 by that direction. And so this is the area that I'm going to say has the deflection. This area right in the middle here. It has the deflection. It ramps up, if you will. It starts pulling on each one of these zones here. In this case, this is supported by this head. And I am not sure that this is totally like that. We wouldn't know because NIST destroyed that evidence. NIST tossed it in the air, if you remember. So we won't know that. You know, they can come up with whatever they want to, but we saw the video. I have the video, link below. It shows them tossing the metal, the steel that's in here, onto the ground. So they're going to make up their own narrative. At that point, I knew that it was just, you know, whatever. NIST representatives, NIST, doing that. So now I want you to section this, when I talk about section, all the way back. So you can move this aside now. Considering this would be my cantilever effect. If it gets worse if you don't consider it and you come back to here. But considering that, you're going all the way up to this one. And now you got your sag area. But resist it by in here, this number 4 that was taking its own little span issues. It now has to take this on because there's no extra reinforcement here that creates a beam. It now has to take on this span, and the midspan from here to here, if you can visualize it. And this will be my critical shear zone, my cantilever. And this will be the cantilever above the head, theoretically. But these heads are very weak, this design, because it just slips over the heads. So this is probably not true, except for it does look like it's kind of behaved that way at the lady took the photograph 3 weeks before. That's a deeper dive for you, but I want you to see the what's going on here. And now that's just one section. Imagine, so section it, multiple 13 inches or 12 inches, whatever what it truly came out to be. And remember, you've got 13, I think, and 12 mixing with each other. So you got some staggered steel here, because I recall, 100% recall, they're saying 13 inches and then also this 12. So those aren't going to line up. No matter how you try it, they're not going to line up ever. They got to be 12 and 12s or 13 and 13. They could have did 13 and 13 per ACI 1977 code. I do have the book. I have researched that. It's funny. I could reach and really say, well, they could extrapolate to my cantilever behavior. I could reach in a 77 code and say, you know what, is this alluding to that? It's not clear, but I can reach. So even though I'm saying it's mine, I can actually find somewhere in that code where I could say, could I reach from here? They're so vague with their behaviors that I could reach if I wanted to debunk myself or fight against myself. But it's never clear as I'm making it. That is clear. Cantilever, behavior. Cantilever, 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 cantilever. All right? And now you look, these cantilevers, the concrete runs up to it. It's a rigid point. Some of it flexes, some of it doesn't. So very critical in this is that you see the offset. So here is this one. It's missing. I'm going to line it up with this center line of the one above. Center, well, it can only move right there, center. And as you can see, it misses the critical shear zone. So it doesn't get to share. Over here it does, though. The load from this one, that's the wind up on this one. So some rigid behavior. But you can see what happens there, that it's got a profile to it. As it's over here at the outside edge, it's almost aligning with this one. But nope, it's extra stress loading here. They're not lined up behind each other, such as this one. This is like only a few inch offset. See the offset? Not much, but a few inches, like 6, I think it is. So or maybe that one's the 8 one. I think it's 2 down below, 6 here, and an 8 there. But you can see that that was a beam going across concrete, right? It is a floor beam. The whole system is just a bunch of beams, the floor slab. And then it becomes two-way action, one-way action based on some other rules. But so you can see you're going to get a lot of rigidity across these two. So now if you run your floor this direction, it skips this, it misses it. It's quite a few, large significant section misses it from the outside edge of here to the outside edge of this one. And so that's a section there that's going to behave differently than if it's over here. Because now, as it comes from this area, remember this is my bias, this critical, this cantilever, so I'm stopping there. You can push it back here if you don't like my bias. But it comes across this head area, this critical shear zone. Remember, this is not, this has some stiffness to it, but out here is not equal to in here. All right, so out here it's going to have some behaviors different than right here. Then it comes over here, it misses this head altogether, but now it loads between these two. So you can see where you're getting a profile that is a masterful, wild profile that I'm trying to help you visualize. I don't know if I did it here. I don't want to go any more, drive you crazy with more of these, but I want you to see how you can section this and you can start working on it. For example, over here, you can start working on that, on counting the butterfly, but you can start working on that deflection that was at the planter box. So I know it's a flat plate slab system, but I want you to just realize that a flat plate slab system they're just a large beam, a flat beam, with a weird engineering, if you will, on the reinforcement. They can go 2 directions, 1 directions, or multiple reversals of directions. because of the concrete and rebar behaviors. And there's temperature steel at the very top, but that's the top steel in the deflective zone, the tributary area, where that would be better to have the stronger steel at the bottom, the more rigid steel at the bottom and not at the top. But I want you to see this interlock here. So here's your number 4. Here's your 5/8 at the top, 5/8, and they put number 4 at the bottom. Again, section that all the way over to the wall. Went to the building wall, from the south wall to the north wall, the building wall surface. But you're going to get intercepted by the BMAs at the deck. You'll see that they then have their own 90s to them. They got turn-ups and then more 90s. I know you guys saw that one video that Bell guy did. He just has it going over to the building and ripping off. Obviously, he's just, stole my content and with the deck ledger failure, but he didn't understand that he didn't have it. He intercepted. He had to go all the way to the building and start pulling off the entire face of the building, all of them, all the way down to O. And that's not what the video even presented as. So the O column. So here's your hooks up top. Now they create these hooks. I'm just showing you the hooks because it just shows you what the blowout looks like in the back in the cone shape. It's not. I'm not trying to say they engage it better. It just gives you that what's left behind the X. Because all I care about is pull out. When I do these pull out tests, all I care about is the pull out. The anchor is nice if you've got breakage. This anchor would be nice. The 90s, these L shapes. If you got some fractures in here, this does act like as an anchor back there, a washer, if you will, a washer and nut. If you got breakage. If you don't breakage, you've got good bond, you're golden. With that said, I think I'll put that in this video about the column. Yeah, I guess I should. I'm just going to talk to you here about it. The column in the parking garage area, the reinforcement, the rebar didn't fail. The rebar did not fail. As you see in these images, this one and the next one, the rebar is 100% intact. There is no failure of the rebar. It's the concrete and rebar marriage failure via deflection and bond break of the rebar in concrete from excessive loading or span issues. And then of course we have penetration, overloading with the slab. So we've got multiple attacks on this. They appear to be the same lengths. There appears to be no fractures. They didn't get shortened and fracture. The rebar didn't fail. What failed is the bond between the rebar and the concrete, the marriage, and that was done through deflection and breaking up this beam. Remember I said look at this as a beam. I want you to section the floors everywhere. And if you look at it as a beam, you'll see that as you section the floor, you'll see that there's no stirrups here holding it together. There's no stirrups. So what holds it together is the one thing ACI says concrete is terrible in, and that's in tension. So what holds this top piece and this bottom piece together? The concrete between here and here, the paste, the mortar mix, the tension of the concrete's ability to bond. That doesn't make sense, does it? So when you get deflection of this deck. This may be more rigid up here at the critical shear heads because it's 5/8 steel sticking out, transitioning over to number 4 steel, I think in the top there too, and you get this deflection of the deck. I'm going a little liberty there, and you get some rigidity here. This deflection creates a bond break that's cycling over and over again. Then you get a core sample in there, and you see where it looks like a teeth been grinding. Well, the bond break is taking place. It never took place properly. Remember, I talked about another one where the formwork is problem is during the build. Alright, that's it for this video. I think, hopefully I didn't lose you too much. Oh, and I had to add to this video. This is adding to it, because I had a previous video I put up similar to this one, and someone tried to troll me about there's no rebar that goes up here. And I thought, you know what, I challenged them and had a little fun with them, then they disappeared. And that's why I'm doing this edit video, because maybe other people think the same thing. So now it's going to be very clear that rebar is over the face, is into the concrete up here. It's going to be very clear in this edited version. That said, let's see if we got a little shout out from our boy here. Brucey. Bruce. Bruce. Good boy. Good boy. There's our shout out. Take care, guys. Yes, they answer like doggies. I know it's blown out likewise, but I kind of like the coolness of it. The kind of cool look. Take care.